All right, hello AP Statistics. This is section 3.2, linear regression and residuals. We'll see how much video we get through this section. We may have to break it up into a couple parts. Big thing though is you need a graphing calculator. Have that out, have it handy along with your note sheets, okay? But you will be using your graphing calculator quite a bit in this section. All right, here we go. First of all, it is a definition. It says a regression line relating y to x has the equation in the form, and I'll write it like this: y hat equals a plus bx, where y hat is the response variable for a given value of the explanatory variable x. All right, so first awkward thing is you see this little hat above the y. Do you have to write that? You do. Does AP expect it? They do. Will they mark it off if you don't have that there? They will. All right, so make sure you have that. That's identifying your equation as a prediction equation. All right. Second, some people say, you know what? This is supposed to be a regression line. I don't write lines in this form. I write them like this. Is that okay? I will say that in context, you probably won't see that very often in this statistics book or most of the other ones that you see. This is true. That is slope-intercept form. That's what you learned in most of your math classes. Okay. However, in statistics, we write it with the intercept part first in this expression to the right. And we don't represent with a B, we represent with an A. Okay? And then the slope component comes second. And your slope, which is in front of the X, just like before, is not M. In our case, it is a B. Okay, so kind of get used to that new context in terms of how we write our equation of a regression line. Okay. All right, this part in yellow is a very important definition. However, it's not going to make quite sense just yet. Okay. It says the least squared regression line of y on x is a line that makes the sum of the squares of the residuals as small as possible. All right. Now, a big word there is residuals. You're like, I don't know what that is, and you shouldn't know what that is. We're not going to learn that until the end of this section. Okay, the end of 3.2. And once we address that, then I'll come back to this yellow definition and try to make some sense of what this means. Okay. All right. So I have the same problem, and I have the points that were graphed a couple days ago in 3.1. Okay, and that was the data that you see right over here. Okay, and if you don't have this in your calculator, take a moment, hit pause, and put that in your L1 and your L2. We're going to do some stuff with it. Okay, now the thing that we're going to do is we're going to find the equation of the line that fits those points best. Okay, there's going to be some equation that has the most precise y-intercept or vertical intercept and the most precise slope that would fit those points better than any other line possible. Okay, and what that means is I have to have a good value for B and a good value for A when I consider this representation of a linear regression line. Okay, so here's what I'm going to do. I'm going to use some work that we found a couple days ago. Notice that this S of y is the standard deviation of y over the standard deviation of x times the r. That was work that we found in 3.1 from our 1var stats. Now, hang on tight. Before you look up your old notes, we also need your y bar and your x bar, which is also from your notes. All right. Now you can go back and you can look at those, okay? Or I can just give them to you in here in red. Okay, so those are it. Okay, but again, you could have just put those in your 1var stats for your L1 and your L2 and figured those out from the couple days ago that we did that. All right, now here's what it says. Find the equation of the, and this is abbreviated and this is allowed, the least squared regression line for golf scores based on temperature in degrees Fahrenheit. Okay, so very simple. I know it takes this form. I'm going to write it on top. Y hat equals A plus BX. And I'm going to find B first. There's my B, is equal to R, negative 0.9899 times, and let's see, I have S of Y, which is 6.546, all over the standard deviation of X, which is 10.429. Okay, so I'm going to write that out, type it in my calculator, negative 0.9899 times 6.546 and divided by that 10.429. I don't know where there's a, there we go. 10.429. All right, and if we do this right, I think we get negative 0.6213, and there's a lot of threes after that. I'm just going to stop right there. Okay, so that is my B. And I'm halfway done. Okay. If I'm going too fast, hit pause. Okay, get these numbers right in your calculator, and just make sure that we finish with this together, negative 0.6213. All right, now your A, okay, is this formula here, y bar minus b times x bar. So y bar is 74.8 minus your b, which we said was from the previous piece. Okay, I'll put this in parentheses, negative 0.6213. Okay, and then times your x bar, which we said was 94.9. All right, so we'll put this in our calculator, and that's 74.8 minus, in parentheses, negative 0.6213, okay, times 94.9 gives you 133.76. Okay, and now I have the important features of my least squared regression line. And again, this line should fit these data values better than any other set. Okay, so here's what I'm going to do. I'm going to write the equation. I'm going to put my hat here like I said I would. My A is 133.76, okay, plus, and then I'm going to put my B in, negative 0.6213x. Okay, and x is equal to, well, let's see, it's the temperature in degrees Fahrenheit, and your y hat is your golf score. Right. Now, some people are like, wait a minute, this was the answer. Do I have to include this x is equal to and y is equal to? It's already written down here. The answer is a big fat yes. That is not only a yes, but this is a fat yes. Okay, you do have to write your x is equal to and your y hat is equal to. You don't have to write the word prediction, of course, because if you have that hat here, then we already know it's a prediction. But you have to write everything here. I'm going to try not to mess this up. In this box, I'm going to call it a green box. This is your complete answer. You don't have to write the yes, of course, but that is that. Okay, that's your final answer. This is the work that's needed for it. Okay. Now, next piece. Now that we have the equation, it is not uncommon to have you describe the slope b. Okay. Now, I need something more than this, saying, okay, b is equal to negative 0.6213. That doesn't tell me what's going on in context of this story. Okay, now here's how I have to do this. All right, and so I do this as a very slow process. The first thing I do is I put a 1 underneath it. I make it look like a slope, and chances are it's not going to be written as a fraction to begin with, so put a 1 underneath it. And then I want you to think about what slope is represented by when you first learned it in maybe your Algebra 1 class. Okay, and most people say it's y2 minus y1 or over x2 minus x1, or maybe the change in y over the change of x. And that's what I'm going to write here, the change in y over the change of x. Okay, now, what does that mean? Okay, and here's the sentence I'm going to write for that, which is expected, okay, by your AP graders. And it goes like this. I'm always going to start with x, okay, and it's basically an increase of one x value. So for every 1, okay, now increase in x is temperature, okay, 1 degree temperature increase we predict, okay? Now let's think about this. This is negative. Since it's negative, I'm looking at the top now. Okay, I have my comma. I'm now going to start talking about the y. We predict a decrease in, I guess, strokes, if you want to say that, or score for Michaela's golf. Okay, so let's point out some important features here. Okay. For every 1 degree temperature increase, this part here is my x. Okay, that's the part in the bottom. It's always a 1. I always put a 1 there. Okay, this word predict is a game changer for people who do this work almost completely right and they forget that word and they drop a full point, which sometimes is 25% of their grade for this question because they forget this word. Remember, there's no guarantee that she's going to actually have a score based off a certain temperature. It's just a guess. It's a prediction. Okay, so we predict. Now, we chose decrease here because it was a negative value. Okay, it was a negative slope here. And then the second part here is your y. Okay, so for every 1 unit increase in temperature in this case, or 1 degree increase in temperature, we predict, okay, in this case again, it's a decrease because it's a negative, okay, in Michaela's golf score. Okay. All right, now again, just a prediction, and that's why I asked the questions here the way I did. It says predict Michaela's golf score while playing in 96-degree Fahrenheit weather. Okay, now I know what she actually did in 96-degree weather. That's this point here. I think she got, I don't know, a 73 or 74. Our chart will tell us that. But anyways, let's figure out what it should be, okay, based off a prediction. And what I'm going to do is this. I'm going to write my equation, okay, the equation that I found right here. It's my y hat, okay, and I'm going to put some parentheses behind it and input this value 96. This is not times, okay, this parentheses. It is an input value, like if you wrote f of x, okay, and I put in 2, f of 2. Same idea. And I got 133.76 plus a negative 0.6213, and then my x is 96. Okay, so put this in your calculator, right? 133.76, okay, plus a negative 0.6213. Okay, and then parentheses or a time sign, 96. It's okay to address this as now times because that's what I'm doing. I'm inputting 96 into this x that you see way over here, okay, on my far right underneath me. All right, and if you do all that math, sorry, the jump screen's on me accidentally, you get 74, okay, 0.115. Okay, now you can't really have 74.1 strokes, okay, so you can round, you can say about 74 strokes, but do write this part first, okay, so that we understand that you actually did a good calculation to get this result. And then after that, if you want to round, no big deal. Okay. Same idea for the next one, you're going to input 121 degrees. Now, that's obnoxiously hot, all right, but again, Michaela supposedly does better when it's warmer out. I don't know what her threshold is, but assuming that it's consistent, okay, we would have, and let me write it like this. I just wrote the answer, that wasn't right. Y hat of 121. And actually, I'll do this. I'm going to show you a shortcut. As long as you write this, Y hat of 121, and you have Y hat identified somewhere on that page, okay, like you actually wrote the equation out for it and put a little prediction sign there, then you can just give me the answer, okay, which is 58.58. Okay, now you can't have 0.58 of a stroke, so you could say around 59. Okay, approximate. But make sure you write this part. Okay, make sure you show me the work. All right, extrapolation. Okay, here's the deal. Your prediction line is valid, okay? Your least squared regression line, which is what I see up here, I'm putting it in this little box, okay, is only valid for the domain of the points that you had in your problem, okay? Meaning, I can only use prediction equations for values from 78, which I'm showing here in the bottom of my graph, to 111, okay? So prediction equations only valid for input values within the domain. I'll say the domain of, they're kind of like the scatter plot points that you got. Okay, you can put scatter plot if you want. I'll just put a little S there. So here's the idea. 96 was an okay point to use because 96 is within, and I was able to mark it somewhere in this group, and that's okay. It's in between the boundary of 78 and 111. Okay, that's actually called interpolation. Okay, is when you choose an input point. Okay, within the domain. Okay, now you won't see interpolation probably in your work. Okay, they don't really talk about that. It's more the reverse, which is extrapolation. Okay, extrapolation is when you choose an input value. Okay, that's beyond the domain. Okay, you choose an input value beyond the domain. Now that's just my definition. That's not the author's definition, okay, of the book. And but that's the way I like to write it. Okay, and so if you think about your domain being from 78 to 121, sorry, to 111, 121 is beyond it. Okay, 121, if you were to keep going, is way, way, way out here, and you'd have to put some little dot out there, and that's beyond our range of values. Okay, so our prediction value is only good for the graph that we see where we drew our values. Okay, anything bigger than 111 or less than I think it's 78 is not considered reliable. So we found this value here, but it is not reliable. You can always make the calculation, but it doesn't mean it's always going to mean something. Okay, here's the last piece. It's called a high leverage point. And what it is it's an outlier within your data. So let's imagine that I have all my little scatter points right there. Okay, and there's this line that fits it pretty dang good. Okay, now imagine if I have this one outlier that's like way off to the right and up to the top, but it doesn't really influence the line. It actually, the line goes pretty close to it, if not pass through it. Okay, that is a high leverage point. Okay, it's a special outlier that actually passes through or comes very close to the point. Or sorry, very close to the regression line. Okay, I doubt you'll see it in your book. Okay, I can almost guarantee it. However, I did see it on AP Classroom as one of their questions, and I had never seen it before until last year, and so I looked it up, and this is what I saw. It fits in this section. However, you probably will not have a question on it. Okay. All right, so we found this least squared regression line. We used this fancy little formulas for B and then for A, and we came up with our equation. Don't forget to write your X and your Y. Now, here's something different. Okay, it says find the least squared regression line for golf scores based on temperature in degrees Fahrenheit. Okay, now you're like, all right, I have these. I've done this before. Why would I want to do this again? Because here is a shorter way of doing it. Okay, this is the official formulaic way of doing it. Okay, however, here's a small shortcut. Okay, I will still have to write y hat is equal to a, whatever that is, plus b, whatever that is, sorry, b, times x, and I'll still have to describe what x is equal to and y hat is equal to. But here's a way that you could do it that's a little bit shorter. In fact, you've already done it without maybe even knowing. When you found r, which is the correlation coefficient. I'm going to write down here at the bottom where your screen is, little snapshots. Correlation coefficients. Okay, when you found R, you also found your A and your B. Okay, so just to remind you, you did this in 3-1. If you go to stat first, okay, unboxing that stat, and you scroll over one to calc, go down to 8, like we've been practicing for correlation coefficient, put in L1, put in L2, okay? Make sure your Y1 is there. And again, if you don't remember how to get there, it's usually trace. Sorry, it's not trace. It is alpha trace. So alpha is the blue button. Trace, you're like, where is that? It's on the very top row, almost on the far right, but not quite. Okay, and then usually Y1 shows up. Okay, and if it doesn't, if it gets you to some weird screen, then what you're going to do is you're going to go to vars, yvars, and you're going to hit function, and then Y1. Pause this and make sure you can get to that screen or get to this Y1 one of these two ways, okay? And if you're trying this like 2 or 3 times and it doesn't work, it's probably because you have a little bit older calculator and you'll have to do it this more traditional way. Okay, so pause it until you get it. Once you get it, then return, okay? All right, once you get the Y1, you'll get calculate, and again, here's the old school R that you found, which you can do the shortcut, that's okay. You can do it this way now. And notice that you have an A and a B that matches what we had before. Okay, there's your 133.76, and this is a negative 0.621 times X. X is temperature in degrees Fahrenheit, and of course this Y hat is score. Okay, and it's really for golf. All right, now, as long as you have this Y1 here, okay, which is important, I'm looking at the second screen, as long as you have that Y1 here, it makes this work really easy, okay? And so you're like, I've already done this, but let me show you an even easier way. You could do this. You can write Y1, and you're like, how do you get Y1? Well, same thing as before, alpha trace, hit Y1. And then behind it, don't put a time sign, put parentheses, 96. Okay, and you'll find that you got the same answer after you input it as you did before. It's just a quick method of doing it. Y1, okay, and again, the way you get that is on the second screen, this alpha trace, okay, and it should give you the same answer as before. I will verify that with myself, alpha trace, and a 96. 74.11. And you can do the same thing with the 121 and see if you get something similar. Now, you'll notice that sometimes these numbers are a little bit different. And you're like, which one's the right answer? Well, they're both pretty close, but the one that's probably more accurate is the one that you have here, because you'll notice that your work is not rounded compared to what we did on the previous screen. Okay. So that's that. Again, use this shortcut if you like. Look how fast this screen went. You should feel happy about it. Okay. You're like, is there any other work I need to show? And the answer is yes. Let me show you what you have to write to make sure that your reader understands what's going on with you. I'm going to put this in blue. You must write TI-84, saying, hey, you know what? I did this on my TI-84, and I'm going to write linreg A plus BX. And if you do that, okay, that will satisfy, okay, all the work that we did in this upper piece. See this part I'm writing in blue, kind of near my name? All of that is getting replaced with, okay, what we have here. Okay, so you can write this instead. Makes it pretty easy to do. You still have to write the x equals to, y is equal to, okay? All right, that is linear regression. Enjoy this shortcut. You're allowed to use it every time. Some people are like, why are you showing us the long way? Because there are going to be problems where they don't give you L1 and L2. They won't give you lists. They'll give you this stuff right here. They'll give you these items that you would have to put in here. There's like 2 or 3 questions where they're done that way, okay? Plus, it's important to know where they came from. All right, now here's what I need you to do. I'm going to have you go back to L1 and L2 in your graphing calculator. I'm going to have you add a point based off this one moment. Okay, it says Michaela had a golf game where a match where she, in 86-degree weather, got a 66. Okay, it says add this to your 3.1 data, which is that original data we had. It says plot your point on your graph. I'm going to do that right now on my graph. It says a score of 66 from an 86-degree temperature. So here's 86 degrees, and 66 is about right here. Okay, I mark that in blue. Okay, and they asked, hey, does this point fit the rest of your data? And the answer is no. It doesn't look like it's close to it at all. So no. And this is called an outlier. Okay, different from the one before, like that higher leverage point was an outlier too. It didn't really fit the data, but it didn't do much. It didn't influence the slope at all. Okay, or the direction of the curve that should, or the line that should fit that. Okay, now here's what they want you to do. Go back to your L1 and L2 and add this to your L1, okay, that 86, and this to your L2. And then do another least squared regression line for it. Okay, do the shortcut that I showed you. I'm going to do it as well, and we're going to look at our old equation versus our new one. Okay, so take a moment and hit pause for a second, and then we'll check it out. All right, so here was my old least squared regression line. Okay, and here is my new one. Hopefully you had a chance to do that. Notice I wrote a hat for each of them still, but I just said this is the new. And I still wrote my x is equal to and my y hat is equal to because that's good habit. All right, but I didn't do it twice because they both have the same representations for their x's and their y hats. Now, did things change? Okay, do I have a new y-intercept? Okay, or my vertical intercept? And if you look, yes, it actually declines. Okay, it got smaller. Okay, and then what happened to the slope? Well, you went from the negative 0.62 to the negative 0.5. It actually got a little larger. Now, it looks weird to say larger, but it is increasing. It is actually getting closer to 0. Okay, so the slope actually got larger. Okay, so did it change? Did you have to adjust from your original line that you would typically have here to this new point? Yeah, okay, what happened? Well, the y-intercept dropped a little bit. So instead of being way up here, it dropped a little bit. Okay, and then further, your slope changed. Okay, the slope got a little bit larger. So instead of having a real steep negative slope, it actually became a little bit more horizontal than what it had before. Okay, so because these both changed, because the y-intercepts and the slope change, we know that this is not resistant to outliers. Okay, further, if you look at your R for this, it was negative still 0.775. That's much different from your old R. Okay, this is new. Our old was what? Almost perfect. Okay, something like that. So yeah, this adjusted as well. Your outliers will influence. I'll say there. Outliers are influential. Okay, to both your least squared regression line and your correlation coefficient. Okay, there you go. Let me go back just to make sure you got that. Okay, so yeah, remember what resistant means. It means it's uninfluenced by. Okay, and so what we say is that outliers are influential to both. The least squared regression line, that changed in both domains, both parts, both the y-intercept and your slope, and of course it did change your R. Okay, it made it a value closer to 0.